Hello! In this video, we are going to prove the following theorem. Let I be an interval, f be a function from I to R, and let C be an element of I. If f is differentiable at C, then f is continuous at C. So let's first remind ourselves what it means for f to be differentiable at C and what it means for f to be continuous at C. Now, to say f is differentiable at C means the following. It means that the limit of this function at C exists, right? And that function we're referring to is the function whose domain is I with the point C removed, and the output values are given by f of x minus f of c over x minus c. Now, when this limit exists, we denote the value of this limit by f prime of c, and we call it the derivative of f at c. Now, from the definition of the limit of a function, to say the limit of this function at c is equal to f prime of c means the following. It means for every epsilon greater than 0, there exists a delta greater than 0, such that for every x in the domain of our function, I set minus c, if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus f of c over x minus c minus f prime of c is less than epsilon. Okay, so that's what it means for f to be differentiable at c. So then now let's remind ourselves what it means for f to be continuous at c. By definition of continuity, this means the following. It means for every epsilon greater than 0, there exists a delta greater than 0, such that for all x in the domain of our function f, so for all x in I, if absolute value of x minus c is less than delta, then absolute value of f of x minus f of c is less than epsilon. So, we're going to prove if f is differentiable at c, then f is continuous at c. And the way we're going to do it is we're going to go directly from the definitions. Right? Another way you could prove it is you could prove it using properties of limits, but we're just going to do it directly from the definitions. So let's get into the proof. So we're trying to prove if f is differentiable at c, then f is continuous at c. So to prove that, let's suppose f is differentiable at c. From here, we're going to show that f is continuous at c. And to show f is continuous at c, what that means is we want to prove that this statement is true. And since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. And from here, we want to find a delta greater than 0 such that this is true. Now, we know that f is differentiable at c, which means we know that this statement is true. And this statement works for every positive real number. So in particular, it must work for the positive real number 1. So if we apply this statement to the positive real number 1, then there exists a positive real number, I'll call delta prime, such that for every x in I set minus c, if 0 is less than absolute value of x minus c, which is less than delta prime, then absolute value of f of x minus f of c over x minus c minus f prime of c is less than 1. Now the claim is, if we take delta to be the minimum of delta prime and epsilon over 1 plus absolute value of f prime of c, then that choice of delta will make this statement true. So with this choice of delta, we are going to show that this statement is true. So to prove this, let's give ourselves an arbitrary element x in I such that absolute value of x minus c is less than delta. From here, we are going to show that absolute value of f of x minus f of c is less than epsilon. Right? As you can imagine, to figure out this choice of delta, you would have ended up doing some scratch work to figure out that this choice of delta is actually going to make absolute value of f of x minus f of c less than epsilon. So now we're just going to show that that's what ends up happening. So first of all, if our arbitrary x here happens to be equal to c, well then obviously absolute value of f of x minus f of c is less than epsilon, right? It's just equal to 0, and that's less than epsilon. So that covers the case x equals c. So from now on, we're going to consider the case x is not equal to c. Now, in this case, we know that x is an element of I, and x is not equal to c. Therefore, x is an element of I set minus c. Also, since x is not equal to c, we know that the absolute value of x minus c is greater than 0. Further, we know that delta is less than or equal to delta prime. Therefore, x will satisfy this inequality as well. So because x satisfies both these two requirements, we can conclude that this inequality is true for our arbitrary x here. Right? So that's going to be used to help us show that absolute value of f of x minus f of c is less than epsilon. So let's see how this ends up happening. So what we're going to do is we are going to multiply and divide by x minus c. But then from properties of absolute values, we could split this up into a product of absolute values, just like this. But now inside the first absolute value, we are going to add and subtract f prime of c. And now we are going to apply the triangle inequality here, which means the absolute value of this guy is less than or equal to the absolute value of this guy plus the absolute value of f prime of c. But as we mentioned earlier, this inequality holds for our arbitrary x. So we can be sure that this guy right here is less than 1. But also note, delta is less than or equal to epsilon over 1 plus absolute value of f prime of c. So, since absolute value of x minus c is less than delta, that tells us absolute value of x minus c is less than epsilon over 1 plus absolute value of f prime of c, which means we obtain this, which is equal to epsilon. And so this shows we have absolute value of f of x minus f of c is less than epsilon, which is exactly what we want. So we have shown that this statement is true, which shows that f is continuous at c. So we have shown if f is differentiable at c, then f is continuous at c. So this completes the proof. And so yeah, that's pretty much it for this video.